Hey y'all, welcome back. Today we are going to continue our unit on sequences and series, and in particular we're going to determine which kinds of series converge versus diverge. We're also going to look at a new type of series, aside from the arithmetic and geometric ones that we've already discussed, and this new type of series is called a p-series. So first we'll talk about convergence, and then we'll get into the p-series. Let me show you what I mean by that. So some infinite series converge, and what I mean by this is that the infinite series has a specific value. We saw last time that some geometric series converge, and we'll talk about that a little bit more. If the series doesn't converge, it is said to diverge. So you don't need to really worry about, checking for divergence. You really just need to check to see, does the series converge? If not, it diverges. So let's look at a couple of series here and just try to determine by adding up the first few terms and trying to recognize the pattern to see whether or not this thing will actually have a value or not. This first one here is looks like a geometric series because we've got a multiplier to the nth power. Now we'll just ignore the formula for right now to figure out exactly whether or not it will converge. But remember that it will converge if the infinite series actually equals a sum. If it doesn't equal a sum, we're going to say that it diverges. So there's a couple of different ways that a sequence could diverge, and we'll just kind of, I'll show you a couple of different examples here. So if I have 2 to the n, that would be like 2 to the first power, that would be the value of the first term, plus 2 squared, plus 2 cubed, plus 2 to the fourth, etc. So this would just keep continuing on forever, right? And so just to kind of break this down a little bit more, so we can actually see the terms, we'd have 2 plus 4 plus 8 plus 16 plus ... So the question is, does this converge or not? Well, this one does not converge, okay? Because as I continue to add this up, the sum will tend towards infinity. Right, like I'm just going to keep getting bigger and bigger values as I stack on these larger and larger numbers. Okay, we talked last time about when it is that a geometric series converges. Although I didn't use that word converge, I just said, hey, this is when this thing will have a sum. And just to be clear here, a geometric series has a sum, or I should say an infinite geometric series. Just, if we've got a partial series, a partial sum, then we're just going to add up the values. But if it goes to infinity, so an infinite geometric series has a sum or converges, that's another way to say it, when the common ratio, or this number right here that we're raising to the nth power, is between -1 and 1. Okay, so it's pretty obvious once you start adding up the numbers that this thing's going to go off to infinity. But if you recognize this as a geometric series and you note that this common ratio, which is 2, is not in this range, then or in this interval, then you know that it's not going to converge. So we say this thing diverges. Now later on, when you get to calculus, it might be important to know how it's diverging. This particular one goes to infinity, right? So if these were all negative, like let's say it was -1 times 2 to the n, and this was -2, -4, -8, -16, and then it would tend towards negative infinity. We don't need to make that distinction right now. Right now we're just saying whether or not it converges. So for this particular one, we're going to say this series diverges because the common ratio is greater than 2, or greater than 1. Okay, remember that it's got to be between -1 and 1 in order for it to converge. So down here we've got actually another geometric series here. This one's kind of an oddball because of what happens. The common ratio does not fall in between -1 and 1. So we know this one's going to diverge, but it diverges a little differently. Okay, this first one went to infinity, but let's see what's going on with this next one. So the first term would be like -1 to the first. The second term would be -1 squared. The third term would be -1 cubed, and so forth. I'll just throw on one more term just to kind of drive the point home here. Oops, there we go. And we'll just say plus ... What's kind of interesting about this particular sequence is that it does not go to infinity or negative infinity. Watch what happens. -1 to the first power is -1. -1 squared is +1. -1 cubed is -1, and -1 to the fourth is +1. So you have this alternating sign here. We could try to group these terms to try to like figure out what the series might converge to. But you know, -1 + 1 is 0, -1 + 1 is 0. So you might think, okay, well, this one actually is going to 0. But that's not really the case, because that's only because I grouped it this way. If I group it differently, like let's say I group this one, and then the next one, and the next one, I have this -1 left over, then it'd be like 0 + 0 + 0 + -1. So because of this sort of paradox of, you know, depending how you group the terms, you're going to end up with a different sum, we say that this one has no sum. In fact, what happens is, as you add one, subtract one, this thing is going to bounce back and forth between, it's going to start at -1, and then when you add the next term, it's going to go to 0, and then adding the next term would be -1, adding the next term would be 0. So it's bouncing back and forth between -1 and 1. So this is what we say like an alternating series here, but we just need to say that it diverges, simply because it does not converge. Oops. Let's see, let's get a text box. So this series diverges. We can just say the common ratio is greater than 1, and that kind of, you know, that answers it as well. But it's a little bit more interesting to say, hey, this thing is going to alternate between two values. Okay, it's not going to settle on a particular value. Well, now the last one is a little bit different, but let's see what's going on there. This one is actually another geometric series. I'm going to scroll down a little bit. Let's take a look at the terms. So we've got 1 over 2 to the first, 1 over 2 squared, 1 over 2 cubed, and so forth. So it's kind of, actually it's the same sequence as that first example, except each term is the reciprocal. Oops. So this is what our series is looking like. We can evaluate each one of these. Let me scroll down just a tad here. And we get 1/2 plus 1/4 plus 1/8 plus 1/16, and so forth. Now, in our last lesson, we actually examined this particular series. Let me show you real quick. Let me bring you back to the notes from last time. Now, this sequence is written a little differently here. You see we've got 1 over 2 to the n versus the 1 over 2 to the n, but 1 to the n is just always going to be 1, right? No matter what you raise 1 to, that is always going to be 1. So this is actually equivalent to 1 over 2 to the n. It's the same sequence. You can actually see in the terms that we're getting the exact same values. And what we showed here is that if we add up all of these terms, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and you just keep adding, this series is going to converge on a particular sum. And that sum here is 1. So we know that this thing is going to converge to 1 because the sum of this infinite series is 1. So whatever the sum is, if there is a sum, that means it converges, and it converges on that value. So we can actually figure that out without, you know, doing that little visual proof. I did give you a formula last time to actually compute it. Let's see here. Where did I write that down? Well, here's one place where I wrote it down. Okay, if the r value is between -1 and 1, and this is just another way of saying that, then we can compute the sum by using this little formula here. So actually, let me go ahead and copy that so I don't have to retype it. So in this case, the sum can be computed by plugging in the value of the first term, which as we see is 1/2, and plugging in the common ratio, which is actually also 1/2. And so 1/2 divided by 1 minus 1/2, which is 1/2. 1/2 divided by 1/2 is equal to the same thing anything divided by itself is, which is 1. So we say that this converges. Okay, the series converges, particularly because r is in between -1 and 1. So if you're ever asked to justify, like, hey, how do you know that a geometric series is going to converge, this is what you should say basically every time, is that it converges because the common ratio is between -1 and 1. And if we want to be specific, we can say, oh, 1/2 is between -1 and 1. So let me go ahead and box that. Okay, so like we said before, geometric series has a defined sum. An infinite geometric series has a defined sum when r is in between -1 and 1. Okay, so that means that when r is between those two values, we can compute the sum, this a sub 1 over 1 minus r like we just did, and that is the value that it converges to. So it should be pretty easy to find whether or not it does converge, and then figure out what does it actually converge to. So let's take a quick look at this series right here. We can identify that this is in fact a geometric series because we've got it's in this form where the n is the power, right? So we've got our a sub 0 times the common ratio to the power of n. Now, if you're not really sure, like if a sequence is written kind of funky like the one we saw above, you're like, hey, that kind of looks like a geometric series, but I'm not sure, you can always check by just like finding the first few terms and saying, hey, do I have a common ratio here? If I divide each term by the previous term, do I get the same thing? Like 1/4 divided by 1/2 is 1/2. 1/8 divided by 1/4 is 1/2, and so forth. So if you're not sure, like if I look at this and like, oh, I don't know if that's geometric, just compute the first 3 or 4 terms and divide each successive term. And if you get the same ratio every single time, then you know you've got a common ratio, and therefore you know you've got a geometric series. So what does it converge to? If it does, well, we know for sure it does. And how do we know that? Well, because the common ratio, which is 0.6, is between -1 and 1, right? This is our r value right here. So we do know that it does converge. I'll just make a little note here. Yes, it does. And the reason we know that it does is because r is in between -1 and 1. So we can compute the sum here, or we can compute what it converges to. The first term is if we plug in 1 here. So I got 4 times 0.6. Now if you're ever, if you're like me and arithmetic doesn't come automatically, just pull up your calculator. Okay, no big deal. We want to figure out what that first term is. We don't want to get it wrong. So let's see, let's move that out of the way. Just a little bit so we can see everything. Okay, so the first term is going to be 4 times 0.6 to the first power. We don't really need to put to the first power, but just to illustrate this a little better. Okay, so we know that our first term is 2.4. So this right now here is 2.4. And then the common ratio is the 0.6. So this is going to compute what this number converges to. So let's see. We got 2.4 divided by, let's make a little fraction here, 2.4 divided by 1 minus 0.6. And we get exactly 6. So if we add up all of these infinitely many terms, we're going to get 6. Now, this isn't the only kind of question I'll ask. This is the kind of question I asked on the last lesson. Just find what the sum is and basically plug in the numbers and compute it. Not particularly interesting, just because all you're doing is just plugging numbers into in a formula. The more interesting types of questions that I think I'm going to ask you here are going to be like this. What values of x will make the series converge? So you have to know what has got to be true about the conditions for convergence on a geometric series. So this kind of question can be it could be really easy, or it could be more complicated depending on what's going on in parentheses here that we're raising to the nth power. Because remember that what we're raising to the nth power, this whole thing, has got to be in between -1 and 1. So that is how we're going to solve this. We're going to say, okay, well, what number does this have to be to make it converge? Now, if r can be between -1 and 1, that means we're going to get an interval of values here. So we're not just going to get a single x value. We are going to get a whole group of x values, actually. So the way we're going to figure out what x has to be in order to make this converge, we're going to set up an inequality that is based on the condition for the common ratio. We say that we know that common ratio has got to be in between -1 and 1. And what's the common ratio here in terms of x? Well, it's just x minus 4 divided by 5. So basically what you do is you'll take whatever's inside here. I mean, it could be something like sine of x. It doesn't have to be real simple like this linear expression. But whatever it is, sine of x might be a little tricky to solve. I'm not going to give you one like that. But it could be something more complicated like a squared or quadratic expression or something like that. And I think I'll show you actually one where that happens, just to remind you how you solve an inequality like that. But okay, so we want x minus 4 is divided by 5. To solve this, we need to first multiply everything by 5. Okay, so if I multiply all three sides by 5, this becomes -5 and 5, and then this goes away. Then the next step would be to add 4 to each side. So if I add 4 to -5, I'm going to get -1. If I add 4 to 5, I'm going to get 9. And if I add 4 to this, well, -4 plus 4 is 0. That's kind of the whole point of adding 4. We want to get rid of that. And so there we go. And that's our solution here. So any number between -1 and 9, if I plug that into x, that means that this whole thing in the parentheses is going to end up being in between -1 and 1, and therefore the series will converge. So that is what our answer is going to be. X has got to be between -1 and 9. Let's see if you remember this from last time. When do arithmetic series converge? Never. There's never any sum to an infinite arithmetic series. So this is a pretty easy answer here, but just in case I could give you like a list of series and say, hey, which one of these converges? If you notice it's arithmetic, it's kind of looking like a linear function, like an mx plus b style equation, you can say right away that it diverges. It does not converge. Okay, it never. Okay, let's take a look at one more geometric series, and then I want to show you a new series called a p-series. So look at this one. This one does not look very traditional in terms of being written like a geometric series, but it actually is a geometric series. When these exponents are offset by 1, don't let that throw you off. Okay, I'm going to show you how to deal with this. Okay, because our common ratio for here is actually going to be 3/4. And again, if you're ever unsure, like you could go to the calculator, for instance. I could type this in to get the term numbers. After I show you how to do this, I don't recommend that you really take this route. I want you to just kind of look at it and know that you can handle it. But I just want to show you real quick. 4 to the power of x. Okay, so if I look at the table, I can see my values here: 3, 9/4, 27/16. Now it's not really obvious, whether or not this is geometric. But if I divide each of these terms by the previous one, I should get the same number. So if I take like 81 over 64 and divide it by 27 over 16, I should get I'll get something that will be the same as if I'm, multiplying all these. Now, what I'm going to show you here, let's just go ahead and do that. Let's see. Can I copy this? I don't know if I can. That's okay. So 81 over 64 divided by the previous term, which, what was it? 27 over 16. I think the common ratio might surprise you, is 3/4. Okay, so just take a quick look back at this here. Oh wait, geez, let me pull that up. Sorry guys. Okay, so just backing it up just a second here. I just realized I didn't have the calculator up. What I'm doing is I put the sequence into y equals, and then I looked at the table to get my terms. This is like term 1, term 2, term 3, term 4, term 5, etc. And basically what I want to check to see is if I have a common ratio by dividing each term by the previous one. So what I just did here was divide 81 over 64 by 27 over 16, and lo and behold, I got 3/4. Okay, which if I get this calculator out of the way, you can see, okay, so we've got 3/4 over here. Let's see if that stands. So I'll just check one more. I'll go ahead and tell you that is the common ratio, but let's just double check. So we've got 27 over 16 divided by 9/4. So let's type that in. 27 over 16 divided by 9/4. And I get 3/4 again. And I could do that, you could keep checking, but I can assure you that this will continue to be 3/4. Yeah, you can see that we're getting the same ratio every time. So that's why it's called a common ratio, by the way. So anyway, we know the common ratio is 3/4, so we know this is geometric, but I just want to show you algebraically how you can manipulate this equation so it looks more like that a sub 0 times r to the n formula. Basically, when you have 3 to the n plus 1, what that really means is that you are multiplying 3 by itself n plus 1 times. Now, if you recall your exponent properties, and no judgment if you don't really remember, because it's been a long time since we dealt with them, but if you have like x to the a times, do I have a time symbol over here? I hope so. Where's my little dot? Okay, well I don't see it on here. Oh, I know where I can find it. So dot, there we go. X to the b. Okay, so when you multiply two powers with the same base, let's see if you remember what to do here. What you end up doing is you add the exponents. So you have x to the a plus b. So this little exponent property is what we're going to do to kind of simplify this a little bit. So if I have 3 to the n plus 1, I can rewrite that as, so if I have 3 to the n plus 1, I can rewrite that as 3 to the n times 3 to the 1, or just 3, right? So, well here, I guess I'll leave the 1 just to kind of show that it's the same thing as this. Okay, so since we have that, we can rewrite this numerator so that it looks like this. We've got, let's see, infinity, 1, and then we need a fraction. Oh, that's not a fraction. We've got a fraction symbol around here somewhere. There we go. So we got 3 to the first, which is 3, times, oh, I just want the times, I don't want all that other stuff. There we go. 3 to the n over 4 to the n. And when I multiply a constant on the numerator of a fraction, that is the same thing as just multiplying the whole fraction by that. So I can actually rewrite this as, so let's see, I'll just throw an equal sign in front of there. I can rewrite this as 3 times 3 to the n over 4 to the n. And another exponent property we have is if we have something like x to the n over y to the n, we can combine those and say that that is going to be x over y to the n. We're going through a lot of work here, which is not totally necessary once you know what's going on here. Let's see if I can get some grouping symbols going here. It doesn't like it. That's okay. No biggie. We'll just do this. All right. So the reason I'm showing you this other exponent property is to show you how we're going to rewrite this. So let's rewrite this one more time. Where this is going to be 3 over 4 to the n. Okay, so now we've got it in that geometric form, right? We just kind of fiddled with the, how this looks by pulling out that extra 3. So in other words, I don't want you to get thrown off by, if these exponents are offset like that, you can use your exponent properties to rearrange it. But really all you need to know here is what the common ratio and what the common ratio is to determine if it converges. Right, and the common ratio here is the 3/4. So if you see these offset, you could just look at this fraction right here and say, hey, that's the common ratio. So now that I've identified that, I can now use my formula. Did I copy it somewhere? I thought I did. Maybe not. Oh wait, here it is up here. Oh, I thought I put it somewhere else, but okay, no big deal. So it's a sub 1. Divided by 1 minus r, okay, which is going to be our first term, which we haven't really computed yet. Let's go ahead and compute that. So if I plug in 1 here, I get 3/4 times 3, which would be 9/4. Divided by 1 minus the common ratio, which is 3/4. Now, don't try to, be a hero and do this in your head, although this isn't that bad. You do need common denominator here and all that. But the safer way is just to go ahead and throw it in the calculator, I think. So let's pull up that calculator. I don't want to forget that this time. And we've got, let's set up this little fraction. We've got 9/4 divided by 1 minus 3/4. And we get 9. Oh, that's kind of nice. Nice little round number here. So this thing will equal 9. So this is a geometric series that converges on 9. Okay. All right, so that's probably enough with this geometric series stuff. Hopefully you understand what it means to converge and diverge. Let's take a look at a different kind of series, the P series. The P series is a series that can be written in this form, where you have 1 over n to some power. So in this case, this is different from the geometric series, because in the geometric series, the n was your exponent, but here n is the base with an exponent that is in a denominator, so you've got like 1 over something. So anyway, this P series will converge if this exponent's bigger than 1. So like 1 over n squared should converge. 1 over n cubed should converge. 1 over n to the 0.5, no, that's not going to converge. So let's determine which one of these series will converge, and they don't look exactly like what's going on up here, but part of this is going to be you understanding how to rewrite these so that it does look like this format. So if we have 1 over the cube root of n, we can rewrite that as, let's see if I can copy one of these that I already used. There we go. we can say that this is going to be equal to 1 over, now the cube root of something, we're really using a lot of exponent rules today, I just noticed. But there is an exponent rule that says if you've got n to some fractional power, so like let's say we have got n to the power of a over b, okay, that's equivalent to saying the bth root, it's kind of a weird way to say it, but the bth root of n, so let's see if I can throw in a root here. Yeah, so we got the, oh, didn't like that. There we go. So we've got the bth root of n to the 8th power. Now the a can either be on the inside or the outside of the radical, that doesn't matter. But so I'll just throw it on the inside, but it could be on the outside. Okay. So we want to rewrite this as 1 over n to the 1/3 power. Okay, and as we write it as 1 over to the n to 1 over n to the 1/3 power, we can say that with confidence that this is not going to converge. It will diverge because p is not greater than 1. In this case, it's 1/3. So that's going to be our description here. Determine if it will converge. No, this series, I'll be more specific here, this p series diverges because p is less than or equal to 1. Okay, and in particular, it's 1/3. Let's rewrite this next one and see if this one is going to converge or diverge. So I'm just going to copy all this. Now, I've got the 4th root of n to the 5th power. So I can rewrite this as n to the power of 5 over 4. Notice that 5/4 is greater than 1. So we can say that this series will converge. So this series converges because p is greater than 1. Finally, we got another one that again doesn't look exactly like this. Sometimes it does look exactly like this and you don't have to do any algebraic manipulation, but most of the time it's going to look a little different just to kind of test your algebra skills here. So we want to say that when you have a negative exponent, once again, we got another exponent property. So if I have n to the power of, let's say, negative a, that's going to be equivalent to 1 over n to the positive a. Okay, so if I have n to the negative 6, that'd be the same thing as saying 1 over n to the 6th. And so since 6 is bigger than 1, we can say that this series converges. Now, we're not going to get into, at least in this course, how to figure out what a p-series converges to. That's going to be something that you talk about in calculus. For our purposes, you just need to be able to tell me whether or not it converges and answer questions like, kind of like this. This is similar to one that we did with the geometric series, but this is asking what values of x makes the series converge. So you have to know that the series only converges when that exponent is greater than 1, the exponent on the n. So if I say, okay, well, what does x have to be to make this converge? Well, we have to say that 2x minus 3 has got to be greater than 1. So when I solve this, I'm going to add 3 to both sides, so I get 2x is greater than 4, and divide both sides by 2, so I get x is greater than 2. So that would be the condition on x to make this series converge. Now it gets a little bit more complicated, and I was kind of hinting at this earlier. If you've got an inequality and you've got something other than a linear expression on here. So here I've got a quadratic expression. So just going to do a little reminder on how you solve a polynomial inequality. So anything that's not linear, you're probably going to want to solve this way. So we've got x squared is x squared minus 4. In order for it to converge, that needs to be bigger than 1. So the strategy here for solving a polynomial inequality is first we want to make it equal 0. or not equal 0, but we want to get 0 on one side. So we got x squared, we're going to subtract 1 on both sides, so we get x squared minus 5 greater than 0. Now from here, we need to make a little number line, okay, and then pick some representative. So here, let's go ahead and make that number line real quick. So I'm just going to draw a little number line over here. Okay, you may recall doing this. I mean, this was a while back. This is like at the beginning of the semester when we talked about solving polynomial inequalities. It might have been like right after Christmas. Not really sure exactly when it was, but okay. So if I solve this one over here, I would add 5 to both sides, take the square root, and what I would get would be, plus or minus root 5. So I'm going to mark those two values on my number line. I'm going to mark positive root 5 and negative root 5. Those would be the values that would make this expression equal 0. Okay, so what I've done here is I've just sort of marked these on my number line, and I need to pick a representative from each one of these and plug it into this expression, and I want to basically just mark whether or not we have a positive value or a negative value. So let's say we plug in like negative 1,000. If I plug in negative 1,000 and I square that, I get a huge number. Minus 5 is going to be pretty inconsequential. So that's going to be positive. So I'm going to just make a little note that between negative infinity and negative root 5, x squared minus 5 is positive. If I plug in something in between here, a convenient value might be 0. So if I plug in 0, I get 0 squared minus 5 is going to be negative 5. So that's negative. I don't only really care if it's positive or negative here. I don't really care what the value is, because what I care about is whether or not this expression is greater than 0 or positive. So far we got this little interval as a solution set over here, no solution set over here. I'm thinking we're going to be likely to get another positive value. So if I plug in like a million squared is a huge number, minus 5 is still going to be positive. So we know that in this interval we're positive. So if we're trying to solve x squared minus 5 is greater than 0, that's going to occur in this interval and in this interval. So my solution set is going to look like this. There's two ways we can write it. If we're using inequalities, we would say x has to be less than negative root 5, or, see if I can move that over, or x has got to be greater than positive root 5. And it is important that we throw in that or, because it's definitely not and, or else there'd be no solution. So there you go. Now that's one way to write it. We've seen that there are other ways of writing this. We can write it as like x is an element of, where's my element symbol? I don't even know if there is one on here. There we go. So x is an element of the set negative infinity, comma, root 5, or negative root 5, and then union, or positive root 5, comma, infinity. Either way you want to write this is fine. They mean essentially the same thing. I just want to give you some choices here. All right, well, that's pretty much it for today. So just to kind of recap here, we went over what it means for a series to converge versus a series diverging. We looked at the conditions for which an arithmetic series converges, which is never, so that's pretty easy. We looked to see what the conditions for a geometric series converging, and we saw that the common ratio has got to be in between -1 and 1 for that to happen. And we also looked at a new series called a p series, which converges when p is greater than 1. So y'all have a great day, and I'll see y'all next time.